Somewhere underneath one of the most productive farming regions in the entire United States, the ground has permanently changed shape, and it is never going back. Not temporarily sunk the way it does every drought before rain eventually refills it. Permanently, irreversibly. In parts of California's Sacramento Valley, the surface has dropped by as much as 20 inches in a single year. And scientists who just finished studying exactly what happened underground say the space that used to hold water down there is now gone for good. This is not speculation, and it is not a slow-moving theory. Scientists are still debating. It is the direct finding of a peer-reviewed study published this year using satellites precise enough to measure ground movement down to the millimeter, and it reveals that a region responsible for feeding a significant share of the entire country just quietly lost part of its underground water storage capacity forever, a loss that will still be shaping how this region manages water long after this specific headline has faded from the news cycle. Today, we are going to explain exactly what researchers found, how they were able to prove the damage is permanent rather than temporary, and why this matters far beyond the farmland sitting directly above it. If tracking real environmental science, not just the alarming headline, is something you want to keep doing, subscribing means you catch the next update the moment new research comes in. Let's start with the basic mechanics of what is actually happening underground, because understanding how an aquifer works is the key to understanding why this particular finding is so significant. An aquifer is essentially an enormous underground layer of water-saturated sediment, functioning in some ways like a giant natural sponge. When wells pump water out of that sponge faster than rain and snowmelt can refill it, the empty pore space left behind allows the surrounding sediment layers to compress under the weight of everything above them, and the ground surface directly overhead sinks slightly as a result, a process scientists call land subsidence. Under normal conditions, that compression is elastic, meaning the ground behaves something like a mattress, compressing when weight presses down and springing back once water returns, and pressure is restored. But push an aquifer too hard, for too long, and something different happens. The fine-grained clay layers within the aquifer can compact permanently, collapsing in a way that closes off the pore space entirely rather than simply emptying it temporarily. Once that specific kind of structural collapse occurs, no amount of rain, snowmelt, or replenishment will ever restore that lost storage capacity. The sponge has not just been squeezed dry, it has been crushed. The physical distinction between these two outcomes comes down to what is actually happening at the microscopic level within the sediment itself. Aquifer material is generally made up of a mix of coarser sand and gravel layers, which drain and refill relatively easily, interspersed with much finer clay layers that behave very differently under pressure. Clay particles are flat and can stack together tightly once squeezed hard enough, and once they lock into that tighter arrangement, there's no natural process that pries them back apart. Refilling the space with water simply is not enough to reverse it. Sand and gravel layers can compress and rebound repeatedly without much lasting change, which is exactly why a moderate amount of pumping followed by a normal wet season rarely causes permanent damage. It is specifically the clay layers, once compressed past their own structural limit, that convert what should have been a temporary recoverable dip into a permanent loss of storage space. That is precisely the transition a team of researchers, led by scientist Stacy LaRochelle, documented happening across parts of the Sacramento Valley, the northern portion of California's Central Valley, in a study published July 27, 2026, in the Proceedings of the National Academy of Sciences, one of the most respected peer-reviewed scientific journals in the country. The team combined several independent sources of data to reconstruct exactly what happened underground between 2016 and 2022. Satellite radar measurements capable of detecting land movement with millimeter-level precision, GPS station data tracking ground position continuously over time, satellite gravity measurements, sensitive enough to detect changes in the actual mass of water stored underground across an entire region, and records pulled from thousands of individual groundwater wells. Cross-referencing all of that data together is what allowed the team to pinpoint not just that the ground was sinking, but exactly when and where that sinking crossed from temporary reversible compression into permanent structural failure. Each of those four data sources brought something the others could not provide on their own. Satellite radar, a technique called interferometric synthetic aperture radar, works by comparing radar signals bounced off the same patch of ground during different satellite passes, detecting surface movement small enough to measure in millimeters, across enormous areas simultaneously, something no realistic number of physical monitoring stations could match in coverage. GPS stations anchored directly into bedrock provided precise, continuous vertical position data at specific fixed points, serving as a reliable ground truth check against the satellite measurements. Gravity satellites, which can detect subtle changes in Earth's gravitational field caused by shifts in underground water mass, gave researchers an independent way to confirm that water was actually being lost, not just that the surface was moving. And well records, gathered from thousands of individual monitoring points across the valley, tied all of that remote data back to actual, on-the-ground water level measurements. No single method alone could have proven permanent damage with this level of confidence. It took all 4 data sources agreeing with each other to rule out instrument error, seasonal fluctuation, or any other explanation besides genuine, lasting structural collapse. The results were stark. Researchers found that the Sacramento Valley crossed that irreversible line in 2021 during California's severe 2020 to 2022 drought, when intensive groundwater pumping pushed portions of the aquifer well beyond what it could recover from. In the years leading up to that point, ground movement across the valley had generally stayed under an inch of reversible compression, the kind of ordinary seasonal flexing an aquifer experiences without lasting damage. Once the 2021 threshold was crossed, some areas of the valley began sinking by as much as 20 inches in. A single year, and critically, that ground did not bounce back once wetter conditions eventually returned. The team calculated that permanent groundwater storage loss climbed to roughly 0.2 cubic kilometers per year during 2021 and 2022, a rate 5 times higher than what researchers had estimated for the years before the drought pushed the system past its breaking point. To put that volume in a more tangible perspective, the valley lost underground storage space roughly equivalent to 30% of the entire city of Los Angeles' annual water use every single year. And that lost capacity is not coming back, regardless of how much rain eventually falls on the region. It helps to picture what that lost storage space actually represents physically, rather than just as an abstract volume comparison. Before this permanent compaction occurred, that portion of the aquifer functioned as a kind of underground bank account, room specifically set aside to hold water during wet years, so it could be withdrawn again during the next drought. Losing 0.2 cubic kilometers of storage capacity every year is the equivalent of that bank account's total available space, shrinking permanently, year after year, regardless of how much water anyone actually deposits into it going forward. The water itself was never truly the irreplaceable resource in this equation. Water can eventually be replenished by rain and snowmelt given enough time. It is the storage space itself, the physical room within the aquifer's structure to actually hold that water, that vanished permanently the moment the surrounding clay layers collapsed. It helps to understand why researchers are so confident this specific damage is permanent, rather than simply another temporary drought-driven dip that will resolve once conditions improve. The team specifically looked for what they describe as an abrupt transition to irreversible damage, a detectable shift in how the ground responds to pumping that marks the exact moment elastic compression turns into permanent structural collapse. Radar observations gave them the clearest view of this transition because satellite radar can track surface movement continuously across the entire valley, rather than relying only on scattered, isolated measurement points the way traditional well monitoring does. By measuring precisely how much the surface failed to recover during wetter years following the drought, the researchers could map exactly where the aquifer had crossed from temporary strain into genuine, lasting structural damage, distinguishing permanently compacted sections of the valley from areas that, while still stressed, retained the ability to eventually recover. This finding carries serious weight specifically because of where it happened. The Sacramento Valley forms the northern portion of California's Central Valley, one of the single most agriculturally productive regions anywhere in the United States, responsible for growing a substantial share of the nation's rice, fruit, and nut crops, all of which depend on reliable, consistent water access to remain viable. Underground water storage functions as a critical buffer for that agricultural system, specifically because it can be drawn on during dry years when surface water from rivers and reservoirs runs short, then allowed to refill during wetter years to prepare for the next drought. Permanently reducing how much water that underground buffer can actually hold does not just represent a one-time loss. It structurally weakens the entire region's ability to absorb the impact of every future drought that follows. At exactly the moment, climate scientists are warning that hotter summers and increasingly unreliable snowpack are likely to make droughts more frequent and more severe across California in the decades ahead. For farmers operating directly above the affected sections of the aquifer, this shift changes the fundamental math behind how they plan for dry years. A grower who has historically relied on groundwater as a dependable backup source during a surface water shortage now has to reckon with a smaller, less reliable reserve than existed just a few years ago, even though nothing about their own water use necessarily changed. That kind of permanent capacity loss also complicates long-term agricultural investment decisions, since crops like almonds and other tree nuts, both major exports for the region, require years of consistent water access to reach full productivity, making growers considerably more exposed to a multi-year drought than they were before this specific section of the aquifer lost its buffering capacity. Here is a detail that makes this finding even more consequential when you consider what California is actually facing in the months immediately ahead. The same region is heading into a winter shaped by a developing super El Nino, a climate pattern new. Research suggests significantly raises the odds of extreme, clustered atmospheric river storm sequences capable of producing severe flooding across the state. Under normal circumstances, a wet winter like the one California may be facing would represent a genuine opportunity to help refill depleted aquifers. Through managed recharge programs, deliberately directing floodwater into the ground during wet years, specifically to rebuild the underground reserves drained during the preceding drought. But that recharge strategy depends entirely on the aquifer still having functional pore space left to absorb the water in the first place. In sections of the Sacramento Valley, where the ground has already permanently compacted, that storage space is gone, meaning even an unusually wet winter cannot fully restore what was lost. A genuinely difficult twist for water managers trying to plan for a season that could bring both extreme flood risk and a permanently diminished underground safety net at the very same time. This creates a genuinely uncomfortable planning problem for California water officials heading into the coming months. Managed aquifer recharge programs work by deliberately diverting floodwater, water that would otherwise simply run off toward the ocean, into specially designed basins where it can slowly percolate down and refill depleted groundwater. Those programs have become an increasingly important part of California's broader water strategy, specifically because they turn dangerous flood surplus into stored drought reserve. But directing that same strategy towards sections of the Sacramento Valley, where the underlying clay layers have already permanently collapsed, would be considerably less effective, since the physical room needed to actually store that recharged water has already been destroyed. Officials now have to factor in exactly which portions of the aquifer retain genuine recharge potential, and which no longer do, a level of granular, section-by-section water management planning that this new research makes possible for the first time. It is worth being clear about exactly what this research does and does not tell us, because the distinction matters for how seriously different parts of this finding should be taken. This is not a prediction about some uncertain future risk. It is a documented, already completed loss, measured directly using multiple independent scientific instruments rather than modeled or estimated indirectly. What remains genuinely useful, and arguably the most important practical contribution of this research, is the detection method itself. Because the team identified a specific, measurable signature marking the transition from reversible to permanent damage, water managers and regulators now have a genuine early warning tool. The ability to monitor aquifers in close to real time using the same kind of satellite radar techniques and catch a system approaching that same irreversible threshold before it actually crosses it, rather than only discovering the damage years later the way this particular loss in the Sacramento Valley was identified. That early warning capability could genuinely matter the next time California, or any other region relying heavily on groundwater, faces a severe multi-year drought. Consider how differently this same situation might have unfolded had this kind of continuous satellite monitoring been fully integrated into California's water management decisions back in 2021, the exact year researchers identified as the moment the damage became permanent. If regulators had access to real-time radar data flagging the specific moment ground movement shifted from ordinary seasonal compression into the early signature of irreversible collapse. Targeted pumping restrictions in just the most vulnerable sections of the valley could theoretically have been enacted before the clay layers there locked into their permanently compacted state, potentially preserving at least some of the storage capacity that has now been lost for good. That is precisely the kind of forward-looking application researchers are hoping this study enables elsewhere, not undoing damage that has already happened in the Sacramento Valley, but catching the same warning signs early enough to prevent it from happening again in a different basin facing similar pressure during the next severe drought. Traditional well monitoring, while useful, can miss stress developing in specific underground layers, since individual wells only provide data at isolated points rather than a continuous picture across an entire basin. The space-based techniques used in this study, satellite radar interferometry paired with GPS positioning and gravity measurements, offer far broader spatial coverage and the kind of precision needed to catch a shift from temporary to permanent damage while there may still be time to intervene, whether through emergency pumping restrictions, accelerated recharge efforts, or other water management decisions specifically targeted at protecting the sections of an aquifer still capable of recovering. If you live anywhere in California, particularly in a region that depends on agriculture or groundwater for daily life, here is what this finding is actually worth paying attention to going forward. Support and stay informed about local groundwater sustainability planning efforts in your area, since California's Sustainable Groundwater Management Act already requires many high-priority groundwater basins to develop long-term plans specifically aimed at preventing exactly this kind of permanent overdraft, plans that depend heavily on public awareness and local water district participation to actually succeed. That legislation passed in 2014, was specifically designed in response to exactly the kind of severe overdraft documented in this new Sacramento Valley research, requiring local groundwater sustainability agencies across the state's most stressed basins to develop and implement plans aimed at bringing pumping back into balance with what the underlying aquifer can actually sustain over the long term. This new research effectively provides those agencies with a far more precise diagnostic tool than existed when that law was first written, the ability to identify not just which basins are broadly overpumped, but which specific sections within those basins have already suffered permanent damage versus which remain recoverable if pumping is reduced in time. Information that could meaningfully sharpen exactly where and how aggressively those local management plans need to intervene. If you live in a region built on compacting ground, be aware that land subsidence can also damage infrastructure directly above it. Canals, roads, bridges, and building foundations can all be affected as the surface settles unevenly, sometimes requiring costly repairs long after the underlying water crisis has faded from headlines. California has already experienced this exact kind of infrastructure damage elsewhere in the Central Valley, where decades of groundwater pumping have caused certain stretches of land to sink by more than 11 feet in total, damage severe enough to disrupt the slope and carrying capacity of major water conveyance canals designed to move water across the state, requiring expensive engineering fixes to keep those systems functioning properly. Subsidence rarely occurs perfectly evenly across a region either, meaning uneven settling can crack building foundations, distort road surfaces, and stress underground pipelines in ways that are not always immediately obvious, sometimes only becoming apparent years after the pumping that originally caused the damage has already stopped. And more broadly, understand that a wet winter, even an unusually wet one, is not automatically a full solution to a groundwater crisis that has already caused permanent structural damage. A nuance this research makes clear even as California heads into a season that may bring significant rainfall. What researchers have confirmed beneath the Sacramento Valley is a genuinely sobering example of exactly how invisible, cumulative environmental damage can become permanent long before anyone standing on the surface notices anything has changed at all. The valley floor looks the same as it always has. The farms are still there, the roads are still there. Daily life above ground continues largely unchanged. But underneath all of it, in a layer of ancient sediment that took thousands of years to form its original structure, part of California's water storage capacity has been permanently erased. And the satellites now watching that same ground closely may be the only reason anyone catches the next crisis like it before the damage becomes irreversible all over again. We will keep tracking this story and the broader groundwater situation across California as new research and new monitoring data come in. If you want those updates the moment they land, subscribing is the way to make sure you do not miss them. And if you live in California's Central Valley or any other region that depends heavily on groundwater, tell us in the comments what changes you have actually noticed in your own community, because the people living directly above ground like this are often the first to notice the signs long before a satellite study confirms them, whether that is a cracked foundation, a canal that no longer flows quite the way it used to, or a well that has needed to be drilled deeper than it once did. Stay curious, and we will see you in the next one.